Welcome back to a lecture series on statistical mechanics and molecular simulations. So recently what we've been doing is looking at the canonical partition function and some of its consequences. Remember, we defined this based on some hypothesis. We said, well, what if rho takes this sort of form here? And of course, we then went in and justified this by looking at a system in thermal contact with its surroundings, right? But when we talked about this normalization constant c, we said that c was equal to the integral of e to the minus beta h over the entire phase space. So this integral spanned the entire phase space. But this is actually not quite correct. And a hint to that is actually if we look at a system with Hamiltonian, so we have a system where the Hamiltonian includes a kinetic part, which contains the sum over all of the magnitudes of the momenta of the system over 2mi, right? Plus interactions with the wall, which is going to be a function of where the particles are. So we have one term that's a function of the momenta, one term that's a function of the walls, right? So this is really just the physical system in which you have a bunch of particles in a box moving around, and notice there's no interaction term. We may have this additional interaction term, but what we've done here is we've assumed it's 0, right? So we have a bunch of particles moving around in the box. Now, to calculate c, we just have to take this integral over the entire phase space of e to the minus beta times this h. Now, of course, here we have then this kinetic part over all the momenta. And then, of course, we have this wall contribution, which is e to the minus beta times psi. And of course, this is integrated over the whole space. Now remember that psi was defined so that it was 0 if the particle's inside the box, and it's infinity at the wall or outside the box. So in the box, we say psi w is 0. On the edge of the box, or outside, psi w is infinity. So that means that our integrals over the x, y, z coordinates of the system, so we have an x, y, and then of course we have a z coming out, those are just going to contribute 0 to the integral. But when you integrate 0, right, you get a number, which will then give you whatever the dimensions of this box is. So maybe this is 0 here. This is the length of the box is Lx. Say Lx. The height of the box is Ly. And the vertical dimension in z is Lz. Now when you multiply them all together, Lx times Ly times Lz, that just gives you the volume. And we've done this before, so that's why I'm moving pretty quickly. And basically what it amounts to is that in this C, we're going to integrate over all of the configurational parts over this term, and what we're going to find is that that integral is just v to the n. Because each one of these integrals over dx1, dy1, dz1, dx2, dy2, dz2, etc., will just give you a factor of v, right? And we have n of those, so we end up with something like v to the n times the integral over the momentum part of e to the minus beta times this sum. And of course, you guys know how to do this sum. We've already done this in previous lectures, and if you don't remember this, just verify it for yourself. But what we found was that this was actually just equal to v to the n times 2 pi m. We're going to assume the particles are identical so that the masses of particles 1 through n are the same. We're going to end up with 2 pi m over beta to the 3 halves. And this is what we got for C. Everything seems okay, right? But what happens when we look at the free energy? Recall that the Helmholtz free energy, F, was defined as, or found to be, minus kBt log C. So what is this? Well, this is equal to minus kBt log of v to the n 2 pi m over beta to the 3/2. When we take the log of all of this, so let's just write this down, log of v to the n times 2 pi m over beta to the 3/2. What we can do is we can use this rule of sums in a logarithm to obtain that this is equal to minus kBt times the log of v to the n plus the log of 2 pi m over beta to the 3/2. Now, of course, you guys know your logarithm rules, so you remember that if we have the log of something to the power, we can take the power and put it in front, right? So here what we're going to do is we're going to take this n, we're going to say this is n log v, and we're going to take this 3/2, and we're going to put it for 3/2 log of 2 pi m over beta. Okay, let's preserve this. So this is f. I'm going to box that. Now I'm going to erase the rest of the board, and we're going to see what a consequence of having the Helmholtz free energy be equal to this is. So let's look at some consequences of this equation. And what I had realized, I had made a slight error here. When we did this integral, right, we got 2 pi m over beta to the 3/2. But we needed to calculate that for all particles, for n particles. So really this should have been 3n over 2. So what we'll do is we'll include that here. It would have been up here, we would have pulled it down at the last step. So now let's think about what this is, right? Remember from thermodynamics, we had this condition that our Helmholtz free energy, which was a function of T, V, and N, right? This seems right? We have T contained in this beta term, we have V in this log, and we have N on the outside of these two logarithms as like a prefactor, right? So this seems okay, right? But remember, we also have this property that if we took the arguments of this function, not these variables which were the equations of state, but if we took the extensive variables and we multiplied them by some constant lambda v, lambda n, then that would mean, in order for us to be a fundamental relation, for this to be a truly defined free energy, this would need to equal lambda times f of T, V, and n. So let's try that. We have our f here, we'll call this f prime. The true f is what we're looking for, right? So let's determine what is f prime of T, lambda v, lambda n. Well, this is just equal to minus kBt, and we're just going to plug in a lambda every time we see one of these symbols. We now have lambda n log lambda v plus 3 lambda n over 2 log, and I'm just going to write beta as kBt, or inverse kBt, so log of 2 pi m kBt. Okay, so let's see what happens here. Well, this is just equal to, we can pull these lambdas out. This is equal to lambda times minus kBt times n log lambda v plus 3n over 2 log of 2 pi m kBt. And it looks like I need to close my bracket there. Now the question is, does this equal lambda times f prime? Well, the answer is no, right? We've been able to pull out a lambda here, but f prime has just log v, whereas here we have log lambda v. So there's something wrong, right? There's something wrong. In fact, we can argue that the StatMech we've developed so far, so StatMech developed so far, is inconsistent with thermodynamics. That seems to be a big problem, right? With thermodynamics. Now, why is this the case? You might wonder, okay, well, is this a problem with how we've developed statistical mechanics so far? Is this a problem with some of our fundamental assumptions or our definitions? Really, what the answer is, and the reason why we're not matching up with thermodynamics yet, is not what we've done with these equations, but rather what we started with, namely classical mechanics. We know that the motions of atoms and particles is actually not classical mechanical in nature. It's truly a quantum mechanical process. So what we're going to need to do is actually make some corrections to this C, right? C, we said as a normalization constant, was equal to this integral over the entire phase space. But this is actually not quite correct. And the reason for that is that because particles behave quantum mechanically, there's actually certain rules they need to follow that will make this integral or this contribution from C smaller. So there's actually less contributions to C. And we'll think about what that means after I erase this board. So in classical mechanics, every single particle can be tracked, right? If we have a system and we have all of these particles in here, we actually went in and we labeled the position and momentum of each particle. We said there is a Q1, a Q2, all the way through a Qn. And not only that, we could label their momentum, a P1, and through Pn, right? Well, according to quantum mechanics, this is actually fundamentally not possible. So the idea in quantum mechanics, in quantum, particles are what are called indistinguishable. Particles are indistinguishable. What that means is if I pick one of these particles out, I may as well have picked any other particle in the system. As long as they have the same, general properties, I can't distinguish between them. In fact, I can't even give them labels like 1, 2, 3, 4 through n, right? So we have a labeling problem. Now, this might not seem like an issue, but let's really think about what this C constant is, right? We said C was this integral over phase space of e to the minus beta h of dqf dpf. But what was a dqf dpf? It was this little volume element in a phase space, right? And the phase space was composed of points, small little points in here that described a state, a mechanical state of nature, right? So a point in the phase space was a state. Is a state. So when we take this integral over the entire space, what we're technically doing is we're counting the number of states. So C is the number of states. The problem with what we've done so far is that when we go and we count our states for this Hamiltonian with, let's say, this n particle contribution to the kinetic part, plus this wall interaction, right? When we go and we count all these particles as distinct particles, what we're doing is we're over-counting the number of states. We're saying that each one of these particles is unique, they all have a unique tag, and I could follow them around indefinitely. Quantum mechanics says no, these are indistinguishable particles, and therefore, we need to not count more states than we should, right? So in this system where we have n identical particles, so if we have this n identical particle system, we need to divide out all of this overcounting of states. Now, how do we do that? Well, technically, right, you can imagine each particle has a label. It has label 1, 2, 3, 4, through n. Really, all we needed to do to divide out the number of states is keep track of how many possible ways that I can label these things. Now, you have a toolbox or a tool in your toolbox for mathematics and combinatorics for this, which is that the number of ways of labeling a set of things is just defined by the factorial. So really, we have n objects, we can arrange them in n factorial ways. So we have n factorial ways to rearrange our labels. Well, in that case, we would say our C should now be divided by all those possible ways of labeling it. So we should say it's 1 over n factorial integral of e to the minus beta h dqf dpf. So this is a quantum correction to this classical partition function, right? And so the question is, what are the consequences of writing C in this way? Well, we know that this integral is the same over the phase space as we had before, so we know that this new C, we'll call it C prime, is equal to 1 over n factorial times v to the n, because inside our psi is 0, giving an e to the 0, which is 1 on all of our configurational parts. Multiplying by Lx, Ly, Lz gives you v, and you have n of those, right? Times this kinetic term, 2 pi m beta to the 3n over 2. I missed the n last time, right? But we now have this n factorial term. So let's see what happens. Well, let's look at, now our Helmholtz free energy F prime is minus kBt times the log of all of this stuff, right? And I'm just going to write it separated out, right? If we have a log of v to the n, we can say this is n log v plus 3n over 2 log, and I'm going to write out the beta as 2 pi m kBt. And now we have this additional term. Remember, if you're dividing, you do minus. So minus log of n factorial. Now we're going to need to simplify this guy a bit. So I'm going to erase the board and then we're going to do the rest of this problem. Okay, so the weird term here is this log n factorial. Now we actually have a mathematical trick for this. It's called the Stirling's approximation. Now in the Stirling's approximation, what it says is that if n is large, which in these thermodynamic calculations, n is typically large. Recall that in a glass of water, you might have on the order of 10 to the 24 atoms in the system. So if n is large, what we have is that log of n factorial is actually equal to n log n minus n. And you can verify this for yourself. Just choose a large n, look at what log of n factorial is, and then compare it to this value, n log n minus n. You can also prove this, it isn't trivial, but you can also prove this, and some of you probably have in your math classes. So taking this is, I guess I should write, this is Stirling's approximation. What we're left with on our f prime is that we're equal to minus kBt times n log v plus 3n over 2 log of 2 pi m kBt. Minus, now we're going to substitute in Stirling's approximation, so we're going to have minus n log n plus n. So let's see what the consequences are. Let's check extensivity again. Let's check the condition that f prime of t lambda v lambda n is equal to lambda f prime of t v n. Let's see if that's true now. Well, all we need to do is substitute in lambdas every time we see an n or a v. So we have f prime is equal to minus kbt times lambda n log lambda v plus 3 lambda n over 2 log 2 pi m kbt minus lambda n log lambda n plus lambda n. Now the first thing we can do is recognize that each term has a lambda in front, just like before, so we can pull that lambda out. So we have f prime is equal to lambda times minus kbt of n log lambda n plus 3n over 2 log 2 pi m kbt minus n log lambda n plus n. Now before, our trouble term was this one. We had a log of lambda n, or sorry, this is log lambda v. We had a log lambda v, and that was our issue, and that's what prevented us from being extensive. But now what we have is actually, oh, and it looks like I accidentally put an extra lambda there. Now what we have is this extra log lambda n term. But recall, I can take this term here. I guess I need to make sure I close my bracket there. I can take this term here and I can actually split this guy up, right? N log lambda v is the same as n log lambda plus n log v, right? It's this term. But the same is true for this term. This is n log lambda plus n log n. So what's going to happen here? Well, inside of this, right, we have lambda minus kbt. We now have, and let's pull out the terms that we like. We have this n log v here, right? And there's a plus sign in front, so we're going to leave that as positive, right? And we're going to ignore this term for a second. Plus 3n over 2 log 2 pi m kbt. That's this term. Minus now n log n plus n. So that's this term and this term. And now we have two terms left over. We have a plus n log lambda, and we have a minus from here, right? We have a minus n log lambda. So our log lambdas actually just cancel out. We can close our bracket there. Well, I have two brackets. And what we're left with is actually just lambda times our original f prime. So now we are extensive. So incorporating indistinguishability of particles makes our Helmholtz free energy f prime extensive. This is big. This allows us to now have a consistency with thermodynamics, which is great. And all we had to do was notice that each of these particles could not be labeled as if they were individual particles. They're indistinguishable from one another. Now there's one more important correction, and it has to do with the uncertainty principle. So let's look at that now. So let's think about what the uncertainty principle says. The uncertainty principle says that essentially, if you have an atom or a particle, you could describe, for instance, its positions in space by some vector, and you could describe its momentum by some vector, right? So we have some vector p1, we have some position vector q1. What the uncertainty principle says is that you actually cannot simultaneously determine both the position and momentum of a particle. We can write that as saying that delta q times delta p, sort of these little discrete sizes in the phase space, must always be greater than or equal to h, which is Planck's constant. What this means is that when you multiply some tiny element of this position space, delta q, by some element of the momentum space, delta p, what you get is a phase space volume that must be greater than or equal to the phase space volume h. So this gives h an entirely new meaning, right? What h is we can say, the resolution of phase space. If you get any smaller than h in that volume, you can no longer distinguish between the particles. The uncertainty principle says so. So essentially, you think when we draw this dqf dpf, we drew these little volume elements, right? dqf dpf. But really what the uncertainty principle says is that this can only get so small. It can only get to the point where it's greater than or equal to h, and I guess if you're shrinking it, it has to then equal h. But when we take our integral, when we say c is equal to e to the minus beta h, and we integrate over dqf dpf, what we're doing is each dqf dpf is becoming infinitesimally small. We're allowing this to shrink down to the tiniest possible volume element in the phase space. The uncertainty principle says no, you can't shrink any further than when this equals h. If that's the case, then we need an additional factor here. We need a factor that prevents us from counting states that are within this box that are smaller than this box. Because when we do this integral, right, we're going to add up the contributions from every possible state in this volume element. These are continuous functions, so you're going to add up all of those states. Well, you actually just then need to divide them out, right? So the way we do this is we say, for this one volume element, let's say it's, for a single particle, it might be dq1, dp1. We need to divide by h. So this should be 1 over h. C double prime now is equal to 1 over h times e to the minus beta. And then you have to do that for every possible degree of freedom. So it's 1 over h to the f. Now what is f? F is 3n, right? So really, we need to divide by 1 over h to the 3n to keep track of this uncertainty principle. Now, if we combine that with what we had previously for our C prime, where the particles were indistinguishable, we now have a complete definition for the canonical partition function. So this is when we're going to truly define this canonical partition function. And we're going to give it a new name, z. Z, which is the canonical partition function, is defined as 1 over n factorial, remember this was from the indistinguishability of particles, times h to the 3n, this is from the uncertainty principle, times the integral of e to the minus beta h of dqf dpf integrated over the phase space. This is the canonical partition function. What is its physical interpretation? Well, it's a normalization constant in our canonical partition function. It is also can be thought of that Z is the number of states in a canonical ensemble. And remember, canonical was a system that was at thermal equilibrium with its surroundings. In other words, it had constant number of particles, constant volume, and constant temperature, NVT, right? So Z is the number of states in a canonical or NVT ensemble that evolve according to Hamiltonian H. Whatever H may be. And of course, these are identical particles here, right? Because we've had to assume that in order to say they're indistinguishable in all this. So really, all we've done here with these quantum corrections is prevented the overcounting of states in classical mechanics. We've realized that we cannot shrink further down than the uncertainty principle allows, and that if we are looking at one particle, we might as well be looking at any other particle, right? So these small corrections actually give us properties where, for instance, our Helmholtz free energy F is now just minus kBT log Z. Or our entropy is equal to minus KB expectation log rho still. Now, of course, the rho has this Z right now instead of the C that we had before. So really, this is what this is really the end of the canonical ensemble. Of course, there's tons of applications of these. They're going to appear all the time in molecular simulation. But next time what we're going to do is actually discuss how we can get to other ensembles. Now, if you're in, for instance, in a certain situation, the canonical ensemble may not hold. For instance, what if you're not in thermal equilibrium, right? What if your temperature is allowed to fluctuate, but you're potentially in something like a pressure equilibrium, where the particle can change its volume to accommodate for pressure changes, so that the pressure stays constant, in which case you have an NPT ensemble. Well, we're going to talk about that. That's the Gibbs, or the isothermal isobaric ensemble. There may also be instances where your box has a fixed volume, but particles are allowed to move between the boundary of the box and the surroundings in order to maintain the chemical potential. This will be the grand canonical ensemble, and we'll also see ensembles in which the energy is allowed to stay constant, which is the microcanonical. So that's just a preface for next time, but based on the physical situation you're trying to model or understand, you might need to be in a different ensemble entirely. Well, thank you guys very much for listening in to this lecture, and I hope that this gives you some insight into how quantum mechanics can help us correct these sorts of deficiencies in our classical approach. So thank you very much, and I'll see you next time.